Thank you. All right. Hey, guys, can you hear me? Perfect. So thanks for making time to come to my presentation. Today I'm going to talk about eliminating data bottlenecks for EDA and AI workloads. So the first thing I'd like to talk about is your actual data center and data and compute trends we're seeing in semicon today. As you all know, advanced technology is driving the need for way more compute and storage, and it's going up at a pretty rapid rate, sometimes even more than Moore's law in some circumstances. Large designs are now taking north of 3 petabytes, as we hear from some of our customers, and compute requirements are growing at over 20% per year. Some folks are even growing at 40% per year, and this is even with really large grids, 100K, 200K cores, growing at some very large numbers. In order to maximize your EDA job throughput in your AI workloads, you need to really utilize and maximize the efficiency of your data center resources. Essentially, what this means is to minimize your GPU and CPU wait times. What you need to do is analyze your jobs, look for clues, see where your storage is bottlenecking you, and try to mitigate that. I found this interesting graph from Intel talking about what they are doing in their engineering compute environment. And this kind of shows the growth of their compute and storage over the years. And as you can see, they're actually growing storage at about 50% and compute at 20%. And they are like in 2016, they were north of 1 million cores in their data center, which is a pretty staggering number. So one of the clues which I like to use and help customers use is looking at CPU to wall time ratio on their jobs. And where you have big differences, that can imply that this is an area for optimization and investigation, and oftentimes storage is a big contributor here. So here are some examples. Compute-bound workloads like a Fibonacci sequence, for example, very little I/O, and you can see real time and user time are pretty much the same thing, so it's going quite well. Create 10,000 files. You would expect that to be CPU-bound, I/O-bound, and it is, because you can see the delta there is pretty enormous. And then the last one's pretty interesting. It's a software build. So I built OpenSSL, and you can see even in this case, 36% delta, which means 36% of the time is being spent on things other than CPU, and oftentimes that is storage. This is an example from one of our customers who was doing tape-out timing on a pretty big design. It was 14 nanometer or 10 nanometer design. And they were running 500 corners of tape-out in that grid. And they shared this graph with me, right? So ignore the red line. I don't really know what that means. They never told me what it meant. But the green line indicates their CPU resource utilization inside their compute farm. 70% is the max here because 30% of the cores were reserved for something else. And you can see over here that they saw lots of ups and downs in their CPU utilization before they installed a fast storage device. After they installed FlashBlade, which is the device that we make, it was pretty much flatlined across the top, so they got maximum utilization. From a runtime perspective, they went from essentially this shaded region down to this shaded region, and I just counted up the squares underneath, and that's roughly a 40% runtime improvement. So a pretty big improvement on tape-out timing for these guys. One of our customers is a big fabless company. They actually recently told us that they are doing over 1 billion jobs a year in their compute grid. That's 2.7 million jobs a day. By installing a much faster storage subsystem in there on some of the worst workloads like verification and cell characterization, they were able to see over a 20% runtime improvement in those jobs. And the way they like to think about that is they can now do an additional 20% jobs in the same schedule, or for them, that's additional 500,000 jobs a day. So you can imagine what that can do to your EDA license cost, improve design quality, doing more sims on the same schedule, and so they're pretty happy with that. This is a high-level flow. All of you know what this is, but so I'd like to point out a few things from the I/O perspective here. In general, what you see in this flow is file sizes tend to increase as you go down the flow, right? So up here in the circuit design, verification space, workloads tend to be a lot of small file, metadata, etc. But as you go down the flows, the files get much, much bigger, and the metadata count tends to go down. It doesn't go away, but it goes down. But from an overall perspective, if you look at what's happening in your compute grid at any one point, you will see it's dominated by jobs of these types, like simulation verification and cell characterization. Some of our customers told us that this is north of 70% of all the jobs in their queue. I don't know if that jives with you guys, but that's what we've been told as well. So one thing to consider is if you have storage which does not have a lot of performance and bandwidth, you have to be cognizant of where you put these different workloads, because it's possible that you can wind up having, say, simulation, extraction, and IREM all on the same storage device, and their I/O can actually interfere with the performance of the other workloads, and we see this quite often, right? So suddenly you'll see your simulation is running 5% slower because someone kicked off a massive extraction job. So ideally, you want to be very careful about how you place data to get maximum throughput if you don't have a fast device. What does the grid look like? You all know this. Standard grid in an EDA company. You have users who submit jobs via some kind of scheduler to a big compute farm, and then that writes to relatively few storage devices. It's very easy to get into the situation where you have lots of jobs running, all reading and writing to the same data set at the same time. And that causes a funnel effect, and it's very easy for a storage device to get choked, with too many I/O requests, and thereby slow down your jobs. So here's some things we hear from our customers, and probably, none of this is new to you, right? EDA tools are really expensive, 5 to 10x the cost of infrastructure often. So maximizing their use, maximizing their utilization is always a high priority. Environments tend to be bare metal Linux, right? CentOS, Red Hat, SUSE, something like that, with pretty low amount of virtualization. I think in my career, I've only come across a couple of companies who are virtualizing EDA tools. 10,000 to 100,000 cores, growing at 20 to 40%, pretty commonplace in our discussions. Disk space use going up exponentially. We're hearing designs more than doubling or even tripling or quadrupling as they go from generation to generation, right? Limited cloud use, but clearly lots of people are dabbling in that space right now, right? So we're definitely seeing people trying to figure out how to solve the problems of going to cloud, licensing issues, data movement, things of that nature, and they are trying to do that today. So that's an interesting thing we're looking at, and we can help support that as well. The other thing is lots of chip companies are doing a lot of software development. And the other interesting part is a lot of the software development processes are also moving into hardware. For example, we now have customers who are running Jenkins farms for RTL, right? So as RTL is checked in, modified and checked in, automatic regressions are kicked off, mini regressions are kicked off, and that's adding even more load. And AI and analytics are picking up everywhere. So some of the profiles, EDA profile looks like, what does it look like? Basically, on an aggregate scale, if you ever look at what's happening, it's millions of small files, very high metadata workload, but it also has large files. This is actually an image from one of our customers' projects. As you can see here, we actually have a histogram of file count by file size, and you can see that 93% of the files are under 16K. We actually have found a number of customers who also make a lot of 0-byte files just to do file-based locking and checking and interesting things like that as well. What's common? Thousands of cores accessing the same data set at any one time. High performance read, write, and delete. So delete is a pretty important workload for chip design processes, because basically you have bots which go in, look at results, delete data, etc. Hundreds of millions, like millions of files of deletes is a commonplace thing, right, at any one time. Sequential and random and storage bottlenecks impact runtimes. But small file and metadata dominated is the general theme for these kind of workloads. So what's needed from storage for good EDA and AI HPC workloads? The number one thing I would say is performance, right? Ability to support high IOPS and bandwidth, an ability to scale that storage with increasing concurrency. So as you add more compute nodes in your grid, make sure your storage can keep up with that demand. something that I call high dynamic range. So high dynamic range is the ability for storage to handle all different types of I/O, metadata, small file and large file, sequential and random. The deletes is a big deal, right? So from a user perspective, all you do is an RM minus R and the data might be gone. But in reality, garbage collection and spaced reclamation is a big deal. And so the ability to do that effectively is important. I actually just did a test before we came to this talk today where I created 1 million files, created about 4 terabytes of space. I was able to delete and reclaim that space in under 2 minutes using our what we call our fast remove capability. Scalability, increased performance, and capacity in a single namespace. You don't want to be having disparate buckets of space, right? You want to keep it all together, and the stability. And someone in the last talk also talked about, how do you manage runaway jobs, and that's a really big deal as well. So you need some kind of clobber protection built into your file system as well. So ideally, you would like a storage system that can scale on a performance and capacity standpoint and handle all these workloads running simultaneously in the same bucket, right? From RTL regressions to synthesis, timing, sign-off, software, characterization, with all these different I/O types all running seamlessly. And come see us at our booth if you're interested in that. So I got some interesting graphs here of what does I/O look like at some of our AI and chip customers. And so I grabbed some screenshots and I just put it here. This is one of our customers, right? They're doing a lot of AI workloads and regressions, about 2,000 to 3,000 cores running in parallel. And they're hitting 560K IOPS and 3 gigabytes per second. This is just a snapshot I just took from a few days ago, right? And you can actually backtrack from these as to what the file sizes are and what the block sizes are. But essentially, this is a very mixed I/O kind of workload, and it's being able to handle that quite well. This is another one of our customers. They have 1,500 individual IP addresses attached to our device right now. So that's way over 1,500 cores. I don't know how many are active at any one point. But this is running software and hardware Jenkins farms, right? RTL regressions and builds, and software, and library and memory characterization. And you can see these fellows are getting close to 10 gigabytes per second of throughput and 183K IOPS. Here's a few more. So this is another one. This is mostly running VCS on a small system, hitting 5.3 gigabytes per second and 270K IOPS. And this is actually a very interesting one. This is we have a deployment in a very large social media company where we have 10,024 GPUs pointing to a few of our storage devices. This is just one of them doing nothing, but all it's doing is deep learning. And they're hitting 9 gigabytes per second of throughput and 750K IOPS. So again, very mixed random, and that's something we see in AI is it tends to be a very random workload, right? Because when the training happens, you're picking up different sets of data randomly for the training to run on. So we actually did a test on Mentor performance, Mentor Quest Ascend performance within Pure Storage. We are actually a consumer of EDA tools ourselves because we do our own FPGA designs. And what we did is we wanted to see how does Mentor Quest Ascend perform under 2 different configurations, something that we call small, which is what we call our 7-blade system, and a medium, which is our 15-blade system. A large for us is 75 blades. So what we had here is we looked at the FPGA and we did some sims on the FPGA. What the FPGA is essentially a 20 million gate equivalent design with 42 megs of SRAM. It has a 32-channel flash controller, PCI Gen 3 4 lanes, DDR4 AES encryption, LDPC, and 6 clock domains. And so the environment in which we tested this was we have our own little grid. So we ran 200 sims in parallel, right? 10 simulations per server, over 20 servers which had 10 physical cores each. So hyperthreading turned off. Hyperthreading is bad for EDA. This workload was mostly right? Because it was essentially generating log files, and we got about 200 gigabytes of data per run. And this is the result we saw, right? So for our small flash blade, we were generating data at around, it was writing data at about 6 gigabytes per second, but at this point it was essentially throttled. This was the limit of what this unit can do. And you can often tell that, by the way. Just look, if you see flat lines anywhere, you're hitting some kind of limit, and we're seeing flat lines up there. Average sim time in this case was 2.9 hours. With our 15-blade system, we got it to 9.3 gigabytes per second, and the simulation time dropped to 2.3 hours. That's a pretty big difference, right? So just by increasing write bandwidth to your storage device, you're seeing a pretty big improvement in overall throughput. The other interesting part was on this particular workload, we saw 5-to-1 data reduction. So our device does inline data reduction, and for these workloads, it was pretty dramatic. So this was the final result. The other interesting part is, what I presented here was average times, but in general, you will always see a histogram of results, right? And there'll be a bell curve of some kind. With the 7-blade system, the small system, the max outlier was at 4 hours for that simulation. Now, these distributions, the reasons for different times are varied, right? Could be NUMA is a big one, right? If you have multi-CPU systems, you have NUMA effect, which can take place and be pretty impactful. But essentially, the max outlier time also dropped quite a bit, from 4 hours to 3 hours. So that can also have an impact. So if you are submitting an entire band of simulations and you care for that entire band to finish, rather than just looking at results as they're coming out, the outlier time coming in is also a pretty big deal. So overall runtime improvement for this config was 26%. And we have a pretty small kind of environment, so in reality, when you're running lots and lots of jobs, you could potentially see this or even better kind of improvements. Talk a bit about AI and ML, right? So this is something that's ticking up everywhere. We're seeing a lot of startups in the space doing AI ML chips. A lot of EDA tools here are trying to bring AI ML into the tools. So what's the center of AI ML? It's data, right? So you wind up doing a lot of data manipulation with different types of data, different types, different I/O styles, etc. And what we see, AI is not just training and inference, right? Before you get to training, there's a lot of work that has to get done. Number one is data acquisition. What data are you going to train on? So in the case of, say, autonomous driving, where we have a number of our customers, they tell us that they are acquiring video data, photo data, telemetry data, GPS data, so all different types of data. But that data is not usable. As they acquire it, it's not usable in that form. They have to do things to it. One of the things is labeling, right? So all the data has to get labeled. So people, they are coming up with AI systems to label data as well, which is kind of interesting. But also a lot of transformation has to happen. So you get a video clip, you only need the first 3 seconds, right? So people have to go in and start modifying the data as it comes in. The other interesting thing is oftentimes training has to be done on a subset of the data based on some criteria. So then this data tries to run in like an Apache Spark cluster or a Hadoop cluster to subset the data to just find it based on certain conditions. Once you have that data done, data curated, what they say, then you want to do model exploration, right? So you're looking at, the data scientists want to look at what kind of model to train on. And there's a lot of experimentation that goes on there with lots of different model types. And finally, at the end, you can start doing your training and then inference. And for this, your storage needs to handle basically the entire gamut of the I/O spectrum. So one of our customers is actually a company called Zenuity. It's based out of Sweden. I think it's Sweden. And they're a partnership between Volvo and Autoliv. And they've actually deployed us in an AI-type workload. And they actually told us, this actually is a little old, this is about 6 months ago, that they had already collected over 20 petabytes of data for this autonomous driving project. And as I mentioned earlier, they actually were trying to do data curation through an Elasticsearch or a Hadoop cluster. But guess what? Those clusters generally require you to move data onto locally attached disks and then do the analysis on that data. But moving this data was like ridiculous. I mean, At 20 petabytes, even at 1 petabyte, at 10 gigabits per second, you're talking about 9 days to move data. That's assuming everything goes well. As this data volume goes up, it's absolutely untenable at that point. So what we are saying and what we're suggesting to customers is that you don't move the data. Where you acquire the data is where you leave the data, right? And then you run all your processing on that. And so these customers now are running things like Spark or Elasticsearch directly on that location where the data is acquired. And that helps speed things up quite a bit. We actually put some of this to our own test to see, how does training work when you're accessing the data directly off of NFS and off of our FlashBlade device. And we actually put together what we call our AIRI stack, which is our AI-ready infrastructure, which is an AI-tuned software stack and hardware stack where we have enabled RoCE, RDMA over Converged Ethernet, and also have a software stack which allows you to do multi-node GPU training. And so we ran the ImageNet training benchmark and for various different models. And so what we have here is, in the first case, we're looking at completely synthetic data, which is essentially data in DRAM inside one of these DGX1 boxes. And a DGX1, if you're not familiar with it, is a device from NVIDIA which has 8 Tesla or Volta GPUs in it. And then we compared it to getting actual data off of a FlashBlade, off of our device. And you can see essentially for every model type, you see almost the same performance as running data from a synthetic DRAM kind of scenario. Now, one other thing which we have enabled is multi-GPU training. So as we can add more and more DGXs or GPUs to the training cycle, and actually you can far exceed data training performance compared to having data in DRAM. So my conclusion is that storage performance can have a massive impact on EDA, AI, and software dev workloads. Customers reported big improvements by installing fast storage devices, and some of the side benefits from that are increased EDA license and compute utilization, improved grid efficiency, improved design quality because they can run way more sims in the same schedule, improved time to market, and lower costs. So my call to action for you guys is find out if storage is bottlenecking you. If it is, figure out where to solve it, and you'll see some big rewards. Thank you. Any questions?
Of course. This is all on-premise today. So
yes.
Do you guys have a sort of, what is your cloud strategy? How would I be able to take advantage of this blazingly fast storage and leverage it in a public utility?
Okay, great question. So the way we're supporting that today is basically through a direct connect kind of scenario where you put your storage device into a co-located data center next to one of these cloud locations, cloud facilities, and then you can essentially have a low latency connection from that storage to that compute, be it EC2, be it GCP compute. And that's something which is going on. Some customers are trying and it's working out pretty well.
Can you talk a little bit about what the implementation, support, maintenance is for your solutions versus, relative to a site that's very familiar with NetApps?
I think those. We are basically a very simple, easy to use device. But for discussions about support and maintenance, I think it's best you come by our booth and we can have a more detailed discussion on that. Any other questions? Okay, thank you.